and welcome to our lesson on solving trig equations. This is actually lesson 1 of 3. There are so many different techniques that we can use to solve a trig equation that we're going to spread it out. Try to handle just a couple of them each day. Now before we get started on this adventure, let's talk about some things we should keep in mind. We did learn all kinds of identities. Those identities, not today, but eventually will come back into play. The identities are useful in making substitutions, generally to simplify our equation before we try to solve. Also, we've reviewed a ton of algebra skills and some that maybe even we haven't reviewed that will come into play, but using the identities to make substitution, using basic algebra skills to solve, those are both things that will be useful. When I say algebra skills, I mean like factoring, or like using inverse operations to isolate something, and we will see some of that today. Also remember that solutions to equations are replacements of the variable that result in true statements, so we can always check our answers by plugging them back in. Also note that when we're solving these trig equations, the answers that we're getting are angles, so we're finding angles. Okay. Now since our trig functions are periodic, what we can end up with here is an infinite number of solutions. It's pretty common actually to have an infinite number of solutions unless we're restricted to a specific domain. Because we can find an angle, let's just visualize the unit circle, right? We find an angle on the unit circle, let's say it represents our solution. Well, I can take a full lap around the unit circle and arrive at that same angle, that same location, but a different angle measurement, an infinite number of times. So it's pretty common for these trig functions that are periodic and repeating and lapping around the unit circle infinite number of times to have an infinite number of solutions. So in general, we're going to be trying to find all of those solutions. Now it's going to be impossible to write every single solution, so we're going to have to try to find a way to describe them unless we are restricted to a certain domain. So unless a restricted domain is given, like if it says not just to solve, but to solve over the interval from 0 to 2 pi, then we don't have to lap around the unit circle. We'll just find the angles that are in that interval from 0 to 2 pi. Okay? So all helpful things to keep in mind. Now first, the simplest, in my opinion, type of trig equations to solve are ones that we can solve by isolating. So the ones we can solve by isolating contain only one term, or only one term in the equation contains a trig function. So for example, I have 1, 2, 3 terms in this equation, only one has a trig function. And that's the same for 1 through 4 here, where if we go to the next page, like this equation, for example, we have 1, 2, 3, 4 terms, and 3 of them have trig functions. And while some of them are like terms, some of them are not, so I'm going to be stuck with multiple terms containing a trig function. So not isolation for something like that. Okay. Now when only one term contains a trig function, we can isolate that trig function, get it all by itself using inverse operations. In the same way we would like solve for x, get x by itself by multiplying and dividing and adding and subtracting. That's what we're going to do here. And we've done a little bit of that already, so this should feel somewhat familiar. So for example, we're going to find all of the solutions in radians to these equations by isolating the trig function. So if I want to get this cosine of x all by itself, I'm going to start by getting rid of the positive 3 out here by subtracting it over. So when I subtract, I'm left with negative 6 times the cosine of x equal to negative 3. And then I'm going to get rid of the negative 6, and then multiply by negative 6 by dividing both sides by negative 6. So that gives me the 1 in front of my cosine. So the cosine of my x has to equal a positive 1/2. Now at this point, it should feel pretty familiar. We are looking for the cosine of some angle to be equal to 1/2. Now I know we could use inverse cosine, but we shouldn't have to here because this is a ratio that appears on our unit circle. So let's go to our unit circle and find the angles where our cosine value is 1/2. So we have cosine equal to 1/2 here at pi over 3 radians. We also have cosine equal to positive 1/2 here at 5 pi over 3 radians. And so those two angles would be our solutions in one lap around the unit circle. However, as I was trying to describe earlier, let's focus on this solution here at pi over 3. I can lap around the unit circle and end up there again. It's a bigger angle, right? The angle that time would be pi over 3 plus 2 pi, but that would be another solution. Or I can lap around another full circle and get another solution. So if I wanted to describe all of the solutions that are at that location, I would say that they would be pi over 3 plus 2 pi n times, where n represents some integer. And then the same thing's happening here at 5 pi over 3. I can loop around the circle and get another solution at 5 pi over 3 plus that full rotation. And then I can add that any number of times to end up at another solution. So if I said solve over the interval from 0 to 2 pi, you're going to say pi over 3 and 5 pi over 3, those are the two solutions. But if I say describe all of the solutions, then we want to make sure we capture all of them every time we rotate around the unit circle, whichever direction. Okay? So let's go back here and say x could be pi over 3. That's one place where our cosine is equal to a half. And again, I can loop around the unit circle any number of times and land there again. And then x could also be 5 pi over 3. And we're going to add 2 pi n number of times to land there again. So this would be the description for all of the solutions to this equation. Okay? Let's try that again over here. So again, I have 1, 2, 3 terms, but only one contains a trig function, so I'm going to isolate that trig function. And this, again, should feel familiar because we've done a little bit of this in our previous module. So if I want to get tangent of x by itself, I'm going to start by adding 1 to both sides. And that means my tangent squared x is going to be equal to 3. And now I'm going to use the inverse of my square, which is the square root. And now my tangent is all by itself. Tangent of x all by itself equal to, just don't forget, is a plus or minus in front of the radical 3. So we are looking for two things. Where is the tangent of our angle equal to a positive radical 3? And where is the tangent of our angle equal to a negative radical 3? And again, that should feel familiar because those are going to happen on the unit circle. So let me go back to this mess that I've created here. Do some erasing. Should have erased this before. Okay, so I'm looking for angles in the unit circle where my tangent is either positive or negative radical 3. Now remember, we get tangent by dividing our sine by our cosine. So here, for instance, if I divide my sine, radical 3 over 2, by my cosine, 1 over 2, those 2's are going to cancel and leave us the radical 3 that we need. So I know that this is going to be one of my angles. Okay, and the same exact thing is going to happen over here at 4 pi over 3. When I divide the negative negative, I'm going to get that same positive radical 3. Okay, so I've got two solutions on the interval from 0 to 2 pi so far. And I could say, let me not get ahead of myself. Let's get the other two solutions first. So not only negative or positive radical 3, but also negative. So the negative is going to happen when one of the coordinates is negative, but I want the same coordinates, right? Take the radical 3 over 2 and divide it by 1 over 2, but positive, negative, that's going to give me the negative radical 3. So then 2 pi over 3 is going to be one of our solutions, and that's also going to happen here. Same coordinates, but one positive, one negative means 5 pi over 3 is going to be a solution. So if I said solve over the interval from 0 to 2 pi, we are looking at 4 solutions. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now we want one nice way to describe like a really condensed way to try to describe all these solutions, right? So let me start with this pi over 3 solution. Okay, this one solution, technically I could, yes, go around a full circle and get to the next solution, but if I go just 1 pi, then I already land at one of my solutions. And then I can go 1 pi and land to my next one, and 1 pi and land at my next one. This picture is starting to look bad. So I can capture all the solutions that would be there in what I highlighted as yellow by saying pi over 3 is an answer plus a pi n number of times. And then the same thing for like 2 pi over 3. So this would be a solution. If I rotate just a pi, I get to my next solution. And then I can rotate another pi and get to my next solution. And then another pi and another pi. So my other solutions would be 2 pi over 3 plus pi n number of times. So these ones gave me the negative radical 3, and then these gave me the positive radical 3. Okay, so let me go here. The positive radical 3 happens when our angle was pi over 3 plus every pi I lap around, I get to another solution. And then over here, this was at 2 pi over 3, plus every pi I lap around, n number of times, I end up with another solution. So this would be the description for all of the infinite solutions to this equation. Alright, moving right along. Let's try the next one. So we've got cosecant. Again, just one trig function in there that we can try to get all by itself. So first I'm going to add 1 to both sides. That means that negative 1/2 times the cosecant of x is going to equal 1. Now technically cosecant is being multiplied by negative 1/2, so I could divide both sides by negative 1/2, but dividing by a half is multiplying by 2. So I'm going to take that approach. Let's multiply by negative 2 on both sides. That's going to give me the 1 in front of my cosecant, which is exactly what I wanted. Cosecant all by itself equal to a negative 2. Now, again, this should feel familiar, but I'm trying to do two things at once here. I'm trying to find an angle, the cosecant of my angle to be equal to negative 2. So I'm looking for an angle and I'm looking for a reciprocal at the same time. Sometimes hard to do. So maybe instead of asking myself, where's the cosecant of my angle going to be equal to negative 2, I know that cosecant is the reciprocal of, let me change colors. Cosecant is the reciprocal of sine. So I could also ask myself, where is the sine of my angle going to be equal to the reciprocal of negative 2, which would be a negative 1/2. So it's the same question, just maybe easier to do one thing instead of two things that we're trying to do here. So if the cosecant is negative 2, that means the sine has to be a negative 1/2. Again, that should feel familiar. That's going to happen on the unit circle. So let's go back to the unit circle, erase the mess, and find the angles where we have a sine value that is a positive, what was positive 1/2? Oh, negative 1/2. Okay, so sine is going to be negative 1/2 right here at 7 pi over 6. And then sine is going to be negative 1/2 right here at 11 pi over 6. And that's not like a nice pi in between those, so we're going to have to go a full pi to get to the iterations of that solution. And the same thing for 11 pi over 6. So if I said to solve over the interval from 0 to 2 pi, you would say 7 pi over 6 is an answer, and you would say 11 pi over 6 is an answer. But I can keep lapping around the unit circle any number of times and end up at that same spot, and so that would be the description for all of the solutions. Okay? So back here. So we're going to say x is going to be equal to 7 pi over 6 plus 2 pi n number of times, and x is going to be equal to 11 pi over 6 plus 2 pi n times. And there would be a description for all of the solutions. Okay? Now, if you're feeling pretty confident here, this might be a good place to pause the video and try this out. Otherwise, let's do this again together. So, I don't know what colors I'm using here. I'm going to try to get my one trig function in this equation all by itself. So first, let me add over this 2 radical 3. That's going to eliminate it from this side of the equation. So 3 times the secant of x is going to equal 2 radical 3. Now I'm going to divide both sides by 3. And so I'm looking for the secant of my angle to be equal to 2 radical 3 over 3. Now again, I'm looking for an angle, but secant's a reciprocal. I'm holding two things in my head. I don't know if I can do it, so I'm not going to try. I'm going to rewrite this. So the secant is the reciprocal of cosine. This means the cosine of my angle would have to equal the reciprocal of what I have here. So that's going to be 3 over 2 radical 3. Now, so that I can find this a little more appropriately, I'm going to go ahead and rationalize what I have by multiplying by radical 3 radical 3. So this becomes 3 radical 3 in the numerator, and then it becomes 2 times 3 in the denominator. Now technically then these 3's are going to reduce and give us something that looks a little more familiar. So we're going to say the cosine of the angle we're looking for is going to be radical 3 over 2. So if the cosine of our angle is radical 3 over 2, that means the secant of our angle is 2 radical 3 over 3 once we rationalize. Okay, so back to our unit circle, we're looking for where is the cosine radical 3 over 2. So again, get rid of this junk. Where's our cosine? Radical 3 over 2, and it was positive, correct? Yes. Yes, just making sure. Alright, so cosine's got to be positive radical 3 over 2 right here. So pi over 6 is going to be a solution. And cosine is going to be a positive radical 3 over 2 right here. So 11 pi over 6 is going to be a solution. And again, not a nice like 180 in between those or something that would be easy to describe. So we're just going to go full laps around our unit circle to keep getting iterations of each of those angles. So at pi over 6 plus 2 pi n, and at 11 pi over 6 plus 2 pi n number of times would be all of the solutions to that equation. So we're going to say x is going to equal, I already forgot, pi over 6 plus 2 pi n, and x is going to equal 11 pi over 6 plus 2 pi n. Alright, so we did it. We're halfway there. This is going to be a longer video, I'm sorry. I put 8 problems to go. Oh, yeah, we'll be able to knock these out, but maybe it's just me. I'm talking too slowly. Okay, let's try the next set of problems. So, as soon as you have multiple terms in your trig equations, you're going to have to change your approach. Like, you can't get two different terms that have trig functions in them both alone, especially if you can't combine any like terms. Okay, so factoring is going to be a useful approach when you have multiple terms that have the same trig function, but their degrees are varying. So if the degree varies, then we're going to try to factor. So what I'm trying to describe there is what we see happening in number 5. So I have only one trig function technically. It's all these terms have the sign, but this one has a degree of 2 and this one has a degree of 1. So I can't just combine those like they're not like terms. I can't combine them and then isolate. So I can't use the same approach. So what I'm going to try to do in a situation like that is factor. And then also, factoring can still be useful if I have multiple terms with different trig functions, but they have at least one trig function in common. So like here, for example, I have 2 different trig functions, but the 2 terms have a common trig function, which means I can try to factor in there as well. So looking for something in common, or looking for multiple terms of the same trig functions with varying degrees. Both going to be places where factoring is going to be useful. So let's try to find all the solutions to this equation. Think about what we do when we have a quadratic. Okay, when we have a quadratic, generally trying to factor, get everything on one side and equal to 0. So that's what I would start with here. If I'm going to factor, I'm going to subtract this sine of x over. It can be subtracted with the sine of x that's here. Those are like terms. And I'm also going to subtract over the 3. Now, it can't be combined with anything, so I just stuck it on the end over there, but technically I want this all to be in order. So I'm going to have my sine squared of x, with nothing combining with that. A negative 1 and a negative 1 makes a negative 2 in front of my sine of x, and then I was bringing over the 3, but now I have my terms all in order and equal to 0. So from this point, we have a trinomial that we're going to try to factor. Now, it's a little weird sometimes to look at it in trig form, so think about if this was a quadratic, okay? So instead of sine squared, maybe I have like a squared. And instead of negative 2 times the sine of x, maybe I have negative 2 times a. And then I have this minus 3 equal to 0. Then what? Well, we'd be looking for factors of negative 3 that make negative 2, like negative 3 and 1. And then dividing by 1 wouldn't change those, so we would see this factor into a minus 3 and a plus 1. And then the factors, remember, are not just useful for factoring. We don't factor for factor's sake. Those are useful in showing us the solutions, right? From here, I know that one of my solutions would have to be 3, and one of my solutions would have to be negative 1. Because if I put a 3 here, 3 minus 3 would make a 0, and 0 times anything makes a 0. And the same if I put a negative 1 here, plus this 1 would make a 0, and anything multiplied by 0 makes a 0. So we call that the zero product property, okay? So these are my solutions technically for A, but I don't really want to solve for A here. Okay, so let me just back this up a second. Let me put this in the factored form, or put my trig equation in the factored form. So remember what we did here in the very beginning. I used a little bit of substitution so that I can wrap my brain around how I'm factoring. And I put this new variable into the picture, right? I put a and a squared into the picture. A replaced the sine of x. So now in my factorizations, I'm going to replace a with, again, what it replaced, which was the sine of x. So instead of a minus 3, I'm going to call this the sine of x minus 3. And over here, sine of x plus 1. And that's what I'm trying to make equal to 0. So I want to make each of these things equal to 0 because then the whole equation becomes 0. So what is it that's going to make the sine of x minus 3 equals 0? That's going to be solution. And what's going to make the sine of x plus 1 equal 0? So this is kind of like what we were doing a few minutes ago. Okay, on this one, if I add this 3 over, I'm looking for the sine of some angle to be equal to 3. Well, I know my sine wave, right? My maximum of my sine wave is 1. The maximum output for sine is 1. The range for sine is capped at 1. So there's no way I can find the sine of an angle to get me a 3 because the max for sine is 1. So since this is not in range, then this is not possible. So we're not actually going to get a solution for the sine of x equal to 3. So not solving, I mean, we're trying to solve there, but it can't happen. Okay, so that's not going to produce a solution. But over here, I think we're going to be able to solve. I can subtract 1 over, which means I'm looking for the sine of some angle to be equal to negative 1. Yeah, that definitely can happen. So where on the unit circle do we have a sine value of negative 1? Sine of negative 1 happens right here. That's where our sine is negative 1. So that would be at 3 pi over 2. And again, I can just keep lapping around the unit circle any number of times to land at that same location. So every 3 pi over 2, we're going to get a solution. So every 2 pi from 3 pi over 2, we're going to get a solution. So we're going to say x is going to equal 3 pi over 2 plus 2 pi any number of times. And that's going to be it. So no solution over there where we have 3 that's not in range, is not possible. But over here, still an infinite number of solutions. Okay, so a little bit of factoring and some of the isolating in one problem. So let's try this next one. This one's kind of nice because we're restricted to an interval of negative pi over 2 to pi over 2. So we don't have to look for an infinite number of solutions. But we're going to use the same strategy. Since I have this quadratic-like thing happening here, I'm going to start by subtracting the 3 over. So I'm looking at tangent squared x plus 2 tangent of x, and then a minus 3 equal to 0. Now, if you can factor straight from that form, awesome. If you need to rewrite this, look at it in terms of a quadratic. You have instead of tangent squared a squared, instead of 2 tangent 2a, and then a minus 3. Then our factors of negative 3 this time that make positive 2 would be 3 and negative 1. Is that literally the same thing? Oh, different signs. Like, we did the same thing twice. Dividing by 1, nothing's going to happen there. So this is going to factor into an a plus 3 and an a minus 1. Now, I don't really want the factored form of that quadratic. I want the factored form for my trig function. So this a that I introduced, it replaced tangent, which means now I'm going to replace these a values here with tangent. So when I rewrite my factored form of my trig function, it becomes, instead of a plus 3, the tangent of x plus 3, and again the tangent of x minus 1, and I'm trying to make this equation equal 0. I can do that if each of these pieces is equal to 0. So now what's going to make the tangent of x plus 3 equal 0, and what's going to make the tangent of x minus 1 equal 0? So I'm going to subtract that 3 over, and where's the tangent of x going to equal negative 3? Well, it's in the range. Remember, our tangent technically goes up and down forever. So we have an infinite range for tangent, so we don't have an issue with -3 not being a possibility. It's just not a possibility that's on the unit circle. So the only way to get this answer is to use our inverse trig function. So x, this is like taking the inverse tangent of both sides, would be equal to the inverse tangent of -3, and that would be the exact form of that solution. The only way to really approximate that is to use the calculator. So what is the inverse tangent of a -3 is about -1.25-ish. Okay, so that's going to be, one solution there. Now, we do have to make sure that our solution is in the interval from -pi/2 to pi/2. I don't really know because what are the decimal forms of those, so let me just check. If I put in a negative calculator, -pi/2, so that's a -1.57-ish. Change colors. This is like -1.57 to +1. -1.57 to +1.57. I just put it in decimal form because I need to make sure this decimal is in that range, and it is. It's definitely in between those, so we're good on that. And then the next one, let me just undo, because, okay, there we go. The next one we should be able to get on the unit circle. So on this one, I'm going to add the 1 over, so I'm looking for where is my tangent going to be equal to +1. Now remember, we're only in the interval from -pi/2 to pi/2. So let me go here. The interval from -pi/2 to pi/2, that's this interval here. Where in that interval is my tangent equal to, I already forgot, a +1. My tangent is going to be equal to a +1 here. That's where I can divide my sine by my cosine and get a tangent of +1. So again, radical 2 over 2 divided by radical 2 over 2 makes 1. So my angle, that's the only angle that's in that interval we're looking at that has that value for tangent. So the one solution is going to be pi/4. For that side of it, we did get the other solution, the inverse tangent of -3. So we're going to say pi/4. So this is an answer, and this is an answer. I'm going to box in both of them. One's in exact form, one's in decimal form, but you get the idea, I'm hoping. Alright, let's try another. So this one says to solve over the interval 0 degrees to 360 degrees, which just means now we're going to have an answer that's going to be in degrees instead of radians. So a couple of defaults. If it just says solve, the default is find all of the solutions. If it says solve over a certain interval, then let's restrict to that interval. Also, if it just says to, or if the interval you're given, or if you're just said solve, again, answers are going to be in radians. If your interval's in radians, give your answer in radians. If it just says solve, give your answer in radians. Unless it specifically says something pertaining to degrees, then we will use degrees. Okay? So the defaults, radians, or all solutions, unless it says otherwise. If we restrict the domain or say degrees, then we'll do those things. Alright, so let's look at number 7. Number 7, I can't do any isolation. I have multiple terms with trig functions, and I have 2 different trig functions in this equation. But I'm going to try the same thing. I'm going to leave my cosine theta and cotangent theta here, add over the cosine theta from the other side, and make this equal to 0. Because these 2 terms have something in common. They have in common a cosine. And if I factor out that common cosine, then I'm going to have left a cotangent of theta plus 1. And once I can get it in factored form, I'm in good shape, because if I can make each of the factors equal 0, I can make the whole equation equal 0. So I'm going to get a solution by figuring out what makes the cosine equal to 0, and I'm going to get solutions here by figuring out what makes the cotangent of theta plus 1 equal 0. Now this is just one lap around the unit circle, so we don't have to go too crazy. So first, where is the cosine equal to 0? So looking at our unit circle, where do we have a cosine value of 0? So cosine is going to be equal to 0 in 2 places. Cosine is 0 here and here. And again, just one lap around the unit circle. So we're going to say at 90 degrees and 270 degrees, we have 2 solutions. So over here, theta is going to equal 90 degrees, and theta is going to equal 270 degrees. And then on this next one, technically we want to subtract that 1 over, so we want to know where's the cotangent of theta going to be equal to -1. So that means we're dividing cosine by sine and getting a -1. So again, back to my unit circle. Where am I going to divide and get a -1? If I divide here, I'm going to get a -1. That's going to be positive. That's going to be positive. This one here is also going to make a -1. So that means that 3 pi over 4 and 7 pi over 4 are going to be two. Oh, we were in degrees. 135 degrees and 315 degrees are going to be two more solutions. So with this one, theta was going to equal 135 and 315, I think. Yes. So we have 4 solutions over the interval from 0 to 360, or from 0 to 2 pi. If we wanted to make that radians, then we could absolutely do that too. Okie doke. Not too bad. Good, we're making good time. Okay, last one. And again, if you're feeling confident, pause the video, try this, see if you can do it yourself. We're going to find all the solutions, or not all the solutions, we're going to find the solutions on the interval from 0 to 2 pi, so back to radians. And then we're back to 2 different trig functions, but if I subtract over that one term, leave this 2 sine squared x cosine x where it is, subtract over the cosine x that's here, then these 2 terms have a common factor of cosine x. So I'm going to factor that cosine x out. Cosine of x goes here. When I factor it out, what am I left with? Well, I'm left with a 2, that's my eraser. I'm left with a 2 sine squared x, and then a -1, still equal to 0. So now that I'm in factored form, sometimes just a GCF is enough to factor. Once I'm in factored form, again, making each of the factors equal 0 is going to get me solutions. So again, where's the cosine of x going to equal 0? We just did that. And now here, where is 2 sine squared x minus 1 going to equal 0? So we literally just did this one here. Where's the cosine equal to 0? But we're in radians. Let me just go ahead and go back. Oops. Cosine is going to be equal to 0, we said, right here at pi over 2 and right here at 3 pi over 2. So 2 of our solutions, pi over 2, 3 pi over 2. So x is going to equal pi over 2, and x is going to equal 3 pi over 2. And then over here, we're going to have to do some isolation. We're going to add the 1 over, and then divide the 2 over. And I'm skipping a little bit of work. I hope we're okay with that. And then we're going to take the square root of both sides. I don't want to skip that one. I don't know why I'm picking and choosing. So the sine of x has to be equal to plus or minus. When I square root this, the square root of 1 in the numerator is going to be 1. Square root of 2, can't do that. So it's technically plus or minus 1 over the square root of 2. If I rationalize that, radical 2 over radical 2, then I'm looking at plus or minus radical 2 over 2, which looks a little more familiar. So that means that the sine of our angle could equal a positive or a negative radical 2 over 2. So to the unit circle, where is our sine equal to a positive or negative radical 2 over 2? In radians. So we have radical 2 over 2 here, we have radical 2 over 2 here, negative radical 2 over 2 here, and negative radical 2 over 2 here. So at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, those are all the angles in the 0 to 2 pi of the interval that I'm looking at, okay, that one lap around the unit circle. So we're going to say x is equal to, again, pi over 4, and then if we want to list them out separately like this, we can. If we want to separate them with commas like this, and say 3 pi over 4, and 5 pi over 4, and 7 pi over 4, then that would be totally fine as well. So over the interval from 0 to 2 pi, this equation has 6 solutions. So imagine if we had to write all of the solutions. An infinite amount, I guess, is an infinite amount, but there it is, okay? So we covered a lot. It was a long one. I'm really sorry. I'm really hoping that when I do this in class, we're going to get through it all in one sitting. So do your best. If you have any questions, always, as always, reach out. I'm more than happy to help. Until next time, take care.